Okay, so we learned about quadratic functions last time, and now today is more about quadratic functions, but involving applications, word problems, everybody's favorites, right? Okay, so let's go ahead and look at these quadratic function examples. And what we're basically looking at here is wording. When you look at a word problem, how do you know what to look for? So the first thing we're going to look at is the Y-intercept. And words that mean Y-intercept in a quadratic application would be something as height. We can say height. So words that would mean the Y-intercept. Where does something start at? What would the height be? Or it could even be, we could say just an initial amount. Amount being anything, the initial height, the initial cost of a product, just the initial amount of something. Okay. And then the method to find a Y-intercept. Well, how do we find a Y-intercept? We let X equal what number?
0.
0. Let X equal 0. Okay, so that's how you find a Y-intercept. You let X equal 0. And then function notation for a Y-intercept. So since we're talking about a quadratic function, remember the quadratic function in its standard form is f of x equals ax squared plus bx plus c. And if I wanted to find the Y-intercept, I would plug in 0 for all my x's, and this would become 0, this would become 0, and we would be left with c. So this is our function notation for a Y-intercept. And I guess I missed one part. It says label it. So our Y-intercept is where you start on the Y-axis, where you intersect the Y-axis. Okay. Next is the X-intercepts. So on a quadratic application, if we are looking for X-intercepts, the main words we should look for is when, and even better, when can also mean time. So whenever you're looking for X-intercepts, it's going to say, when was this, what can we say? So if this is a quadratic function, you can say, what amount of time did we reach the maximum height, or over what amount of time did we reach this initial amount? Anything like that. So whenever you're looking for X-intercepts, you're looking for the words when, or you're looking for the words time. Okay. And then methods to find X-intercepts. Well, to find an X-intercept, we let Y equals 0. Or in function notation, we let f of x equals 0. Okay. And then function notation for X-intercepts. So the function notation, so if you let f of x equals 0, you would get something such as, and again, if we rewrote the standard form, ax squared plus bx plus c, and if you are looking for an X-intercept, you let f of x equals 0. So you would get 0 equals ax squared plus bx plus c, which when we eventually find the X-intercept, we will come out with something such as coordinates, let's just say x1 comma 0 and x2 comma 0. So that would be our function notation. Okay. And label the X-intercepts on this graph. Well, your X-intercepts are where you touch the X-axis. So looking at this one, I would assume there's an X-intercept here and an X-intercept there. Okay. And then last. We know since we have a quadratic function, we have a vertex, and we know what the vertex is. It is the main point of the parabola. So looking at this parabola, this would be our vertex. Okay, and now words that mean the x coordinate of the vertex. So in an application problem, how do we know it's looking for the x coordinate of the vertex? And the words or the phrase you would look for is, x, well, what's the best way to put this? X values that cause the maximum output, or I guess we could say that. We'll say X value that gives us the, I'm trying to put it into English is hard. So we know that if you find the X value of the vertex, you can find the Y value. So if you're looking at an application problem, words that mean you're looking for the vertex means that items that cause the maximum height. So I'm just going to say that. So X value that gives maximum height, amount, what else could it be? Maximum height, maximum amount, anything that's just related to that. Okay, so that's good enough for the X value. Now, if you're looking for the Y coordinate of the vertex, this means we are just looking for max height or the max amount of something. Okay. And then the method to find the vertex, we learned that last time. We know to find the vertex, we do h equals negative b over 2a, and k equals f of h. And then function notation for the vertex. Function notation, I'm assuming, is just h, k. That's it. Okay. So as we work through the next pages, we're going to be looking at the word problems of quadratic functions. So we will see the clues that tell us, look for the x-intercepts, look for the maximum height, look for the x value that will give you the maximum height, and we will solve them that way. Okay, so this page is just all definition, getting us ready for the next examples. Okay, everybody good with this page? For now, right? Okay, so let's try it out. So given this graph, answer the following questions. All right, so number one, the graph models the height h in feet of a small rocket t seconds after it is launched. The path of the rocket is given by the function h of t equals negative 16t squared plus 128t. This wants to know, question A, how long is the rocket in the air? So this means we're looking how long, we are looking for time. So basically, we're looking for the X-intercepts. So how long is this rocket in the air for?
8 seconds.
8 seconds, that's it. So you start at 0 seconds and you end at 8 seconds. So I'll write it down here too, 0 and 8. So this rocket is in the air from 0 to 8 seconds. So we'll just say 8 seconds. Okay. And then it says, what is the maximum height of the rocket? Okay. So by looking at this, if you're looking for the maximum height, this means you're looking for the vertex. So we could just guess it because it looks like everything's going by what? Tens? Right? 210, 220, 230, 240, 250, 260. So we could say it's right between 250 and 260. So we could say that the maximum height is how many feet?
4.
Repeat.
Like
How many feet?
258.
258. That's a good guess. Say 258. You can even say 255 if you want, but we'll say 258 feet. Of course, we can truly find this by using the vertex formula, but this one I think is just an example on how to read the graph. Okay. And then C, what is the height of the rocket 2 seconds after it is launched? So what is the height of the rocket 2 seconds after it is launched? So we look at this 2 seconds and we go up, and let's hope it's a clear enough number. And what is the height of the rocket at 2 seconds?
That 190.
That is 190. And the other question said, is the rocket going up or down at 2 seconds?
Up.
Rocket's going up, right? So we are going up. Okay. So the height of the rocket is 190 feet, and the rocket is going up. Okay. And then D, what is the height of the rocket 6 seconds after it is launched? So same thing here. Find 6 seconds, go up, and let's get on that Y value there. At 6 seconds, it's also at how many feet?
190.
190. But this time the rocket is going
Down.
down. All right. So 190 and down. When is the rocket 112 feet high? So it says estimate. So again, we're just reading the graph. So when is the rocket 112 feet high? So let's look. Let's see our labels. This would be 110. That would be 120. So at 112, let's just put it around here. Go there. And also over here. So it says when, so it wants the X values. So when is it first at approximately 112 feet high? How many seconds?
1.
1 second. And then again, when is it 112 feet high? How many seconds?
7.
7. So 1 and 7 seconds. So when is the rocket 12 feet high? At 1 second and at 7 seconds. Okay. And do you think the rocket is traveling faster from 0 to 1 second or from 3 to 4 seconds? Let's see. All right, I can erase all of these. All right, so from 0 to 1 second, so from 0 to 1, the rocket gets up to 112 feet, right? So from 0 to 1 seconds, we're at 112 feet. And then the question says, is it going faster from 0 to 1 or from 3 to 4 seconds? So from 3 to 4 seconds, it looks like you go from 240 to 258 feet. So 240 to 258. So which one do you think is faster? 0 to 1 or 3 to 4?
0 to 1.
0 to 1. Because in 0 to 1 seconds, we cover 112 feet. In 3 to 4 seconds, we cover, what's that? 18 feet. So 0 to 1 seconds is faster. I'll say in 0 to 1 seconds. In 0 to 1 second, rocket covers 112 feet. Okay, awesome. And then write a reasonable domain and range for this event. Okay. So what do you think the domain, or what do you think a domain that could represent this rocket is? What time does the rocket start at?
0.
0. And what time does the rocket land?
8.
8. So now here's where it kind of conflicts what we learned about last time. We did say the domain of all quadratic functions is all real numbers, but now you put a real world application on it, and can a rocket stay in the air forever?
No.
No, right? So it's got to hit the ground somewhere. So this domain only goes from 0 to 8 seconds. Okay. And then our range, well, before you launch the rocket, how many feet do you start at?
0.
0. And then you launch it, and how high does it go?
258.
258. There you go. There's our domain and range. 0 to 8 and 0 to 258. Okay. Awesome. We'll say C graph. Okay. Everybody go with that one. We didn't have to do too much math, right? Yet. Okay. Next. Oh, this is going to be fun. It's so colorful. All right. Now look at these graphs to answer the following questions. So this graph has lower and delay, the epidemic peak. You have a graph that represents, let's see what we have here. We have this graph that represents uncontrolled transmission. And we have this other graph that represents controlled transmission. All right. And then our y-axis is the number of cases. And our x-axis is the time since the first case. Okay, cool. So A, estimate the y-intercept of both graphs. Where do you guys think the y-intercept is at? So remember that this is your y-axis and this is your x-axis. So your only y-intercept could be down here in the corner, which is what number?
0.
0. Good. So there's our y-intercept for both graphs. That's our y-intercept. So our y-intercept is 0, 0. Okay. And then B says, interpret and compare the vertex of the graph on the left to the vertex of the graph on the right. Okay. So looking at this graph on the left, here's our vertex. And looking at the graph on the right, here's our vertex. So what do you think the difference is between both of those vertexes? And definitely one's higher than the other, but look at the graph, compare them, and try to understand why one is larger than the other.
The domain is wider for the smaller one?
The domain is wider. That could be useful, but we only want to know about the vertex right now, right? Which, yes, if you want to put in that context, this would be the X value for the second vertex. And this would be the X value for the third vertex. So I'll say X1 and X2. So now if you want to talk about X values, well, remember our X axis is representing time. So if we want to talk about it that way, how would you compare those vertexes? And remember, the first graph here represents uncontrolled transmission. The second graph represents controlled transmission. What do you guys think?
Are you talking about like the controlled transmission as far as the epidemic is concerned?
Yeah, whatever
Okay, okay.
however you're reading
Okay.
this. Yeah.
Okay.
Whatever you think, there's no wrong answers here. Whatever you think the difference between these two vertexes are. And all the information is given on that graph. Like, why is the first vertex larger than the other vertex? And there could be a lot of factors here. So somebody give me something.
Is it just like the number of cases and the amount of time? Like the first one, the green
Yeah.
one is a lot in a short amount of time, and then the orange is not so many in like a longer amount.
Yeah, that's
Yeah.
perfect.
Yeah.
So just like you said, number of cases and the amount of time, which if we look at our first vertex, in a short amount of time, we get the largest number of cases. And if you look at the next value for that vertex, in a longer amount of time, we have still a lower amount of cases than you had with the other vertex. Anybody else see anything different? Other than uncontrolled and controlled, right? All right. That works for B. All right. C. Interpret and compare the X-intercepts of both graphs. So for our X-intercepts of both graphs, well, let's see. They have an X-intercept here and here for the first graph. So there's an X-intercept. There's an X-intercept. And then for the last graph, we also have an X-intercept over there. Okay. So interpret and compare the X-intercepts. So what do you notice between the difference of the X-intercepts for the first graph and the X-intercepts for the second graph? And this is understanding what values are given to our X's. Remember, our X is all about time. What do you guys think?
Maybe they both have X-intercepts. I
Well,
don't know.
we definitely know they all have X-intercepts, but what do you notice? What is the difference between the X-intercepts of the first graph to the X-intercept of the last graph?
Well, one has 2 and one has 1.
Well, this one also has 2 because they both
Okay.
start at they both start at 0, 0.
One is
Longer time?
Yes.
One is shorter time.
One is shorter time. So you notice for the uncontrolled one, yes, the cases peaked, right? The cases spiked, but they were able to control that at the end in a shorter amount of time. But then for the second graph, who has the X-intercept at the end, it's controlled and it's able to be controlled over a certain amount of time and not in a shorter amount of time. So I guess that's all we can say, right? Time. We can just put time. Look at you. What is it? No, we'll just say time. This is recorded, right? So the first graph, the cases were controlled in a shorter amount of time. And on the second graph, the cases were controlled over a longer amount of time. Okay. All right. And then D, which of your previous answers tell you about domain and which one tells you about the range? So all this wants to know is out of B and C, which one deals with domain? Does B or C deal with domain?
C.
With that B, or did you say B or C?
I said C.
C. All right, good. So C deals with domain because C dealt with the X-intercepts, and the X-intercepts are all about domain. Remember, domain's all about X values. So C is domain, and that means B has to be
Range.
range. Ooh, man, that was a tough one, huh? All right. Any questions on that one?
And word problems suck.
We didn't even do any math though, right? This was like, look at the graph and compare. All right. Cool. All right, now we do some math. How's that? Okay. So 3. After t seconds, a ball is tossed in the air. The ball reaches a height of h feet given by the function h of t equals 23 plus 144t minus 16t squared. A, fill in the table for the missing values. Okay, cool. We're going to use Desmos for this. And when I use Desmos, I'm just going to rewrite the function as h of x equals 23 plus 144x minus 16x squared, because Desmos doesn't like t. All right. And Desmos, and I need to go to the other version since I'm making a table. And you go there, and you go there, and go back here. All right, perfect. We're gonna type in that function. What's up?
I saw that one of our homeworks was like that. It had like G or whatever. But that when it's like that, it kind of confuses me. So I always change it to X because I just understand it better. Do you like deduct points for that?
No, that's totally fine. Because T doesn't work in your calculators and it wouldn't work on Desmos. So if you want to change it to X, then that's totally fine. Okay. So I type this one in, 23 plus 144x minus 16x squared. Change to my table, and let's go fill in those values. Look at that. All right. So we have 0, 3, 6, 9, 10. So 23, 311, 311, 23, negative 137. All right. Gotta love Desmos, right? Okay. And we're gonna have to make that fit on there. And boom. Okay. So now to answer B. It says, from what height was the ball thrown? So this one is looking for the Y-intercept. This one's looking for the initial height. So if you haven't thrown the ball, how many seconds have passed by?
$23.
Well, if you haven't thrown the ball, remember that T here or X represents seconds. So if I'm standing still with the ball,
0.
0 seconds, right? So this means that, again, this is looking for the Y-intercept, is looking for the initial height. And remember, to find a Y-intercept, you let X equal 0. Well, we did that already, right? If T or X is 0, then what is the height that this person's throwing the ball at?
23.
23. 23 what?
Feet.
Feet. At T equals 0, height, I'm going to say H of 0 is 23 feet. Okay. So this means they're probably standing on a building or somewhere and throwing the ball up. So they're 23 feet in the air before they even throw the ball up. Okay. And then C says, what is the height of the ball at 3 seconds? Well, lucky we fell at that chart already. When time is 3 seconds, what is the height of the ball?
311.
311. So at T equals 3, height at 3 seconds is 311 feet. Okay. And then D. Does the table of values show you the maximum height? What is the maximum height the ball will reach? Okay. So do you think the ball cannot get past 311 feet? And our answer is what? So look on the graph on the left.
Yeah,
What is the
347?
maximum height that this goes up to?
347.
347. So does our table actually show us the maximum height?
No.
No. So guess how we would have to find that? We would be looking for, what's this called? What is this high point called on the graph to the left?
Vertex.
The vertex. No, you need to find the vertex.
Okay, I'm sorry. How did we get 347?
So that is just, since Desmos made the graph, that is the height, that is the highest point the ball will reach. But let's say you don't have Desmos. That's why I'm about to show you that you need to find the vertex. Because remember, whenever you see the words maximum height, that means you're looking for the vertex. So in order to find that vertex, we need to use the formula H equals negative B over 2A and K equals F of H. So that's going to help us find the vertex. So looking at this equation, let me rewrite it one more time in order. Highest power first. Negative 16x squared plus 144x plus 23 And what is the value of A on this equation?
-16.
Negative 16. What is the value of B?
144.
144. So now, if you know A and B, this can help us find the vertex. So we just plug that in down here. And H is going to be negative B over 2A, which gives me negative 144 over 2 times negative 16. That gives me negative 144 over negative 32. And negative 144 over negative 32 gives me 4.5. So what this means is that in 4.5 seconds, we will reach the maximum height. But now we have to find that maximum height. We have to take 4.5 and plug it into the original function. All right. So now you'll have K equal to H of 4.5. And lucky for us, I still have the function up in Desmos over here. So I'm just going to type in 4.5. And you get 347 feet. So at 4.5 seconds, you will reach the maximum height of 347 feet, proving that this XY chart does not show the maximum height. So if you ever come across that question on your homework, if it says, does this table show the maximum height? Well, you want to find the vertex to prove that. Okay. Any questions on that? All right. And then what was the last question? Use the table of values to estimate how many seconds it will take for the ball to hit the ground. Okay. So now this is just looking at our table of values. So it says at 0 seconds, we're at 23 feet. And then we throw the ball. 3 seconds, we're at 311 feet. The ball's coming down. And at 9 seconds, we're at 23 feet. And then at 10 seconds, we're at negative 137 feet. Well, negative 137 feet means the ball hit the what?
Ground.
The ground. So in between 9 and 10 seconds is when the ball will hit the ground. So what is a good estimate for a number between 9 and 10 seconds?
In the middle, 9.5.
That's it. That's what we're looking for. It says, give us an estimate. So we estimate, oops, that is ugly. That's not an E. Ah. So we estimate around 9.5 seconds, the ball will hit the ground. Okay, there we go. Okay, any questions on this one? And if you need help seeing your answers, again, just pull up Desmos on your computer, on your phone, and it will show you the graph. So that's how we found out. We found out by Desmos, and then we also proved it by finding the vertex that our XY chart over here on the right did not show the actual maximum height. Okay. And I guess you could kind of figure that out too, because at 3 seconds, you're at 311, and then at 6 seconds, you're at 311. So between 3 and 6 something had to change. The ball cannot stay at a constant 311 feet in the air. So something to also think about there. Okay. Next. Another ball is thrown into the air. Can we get more creative with these? All right. A ball is thrown in the air. The height of the ball above the ground is represented by the function h of t equals negative 4.9 t squared plus 2.45 t plus 2, where height is in meters and t is in seconds. So A, from what height is the ball thrown? So this is just like the last one. You're looking for the y-intercept. So if I haven't thrown the ball, what is the value of time right now?
0.
0, right? So again, this is another one of those y-intercept problems. And remember, to find a y-intercept, you let t or x, whatever variable we're working with, equal 0. So this means we'll say at t equals 0, h of 0, and if I plug in 0 for every t, that becomes 0, that becomes 0, and at what height am I throwing this ball? How many meters?
2.
2. Okay. So h of 0 is 2 meters. All right. Now B, what is the maximum height of the ball? So when you see these words, maximum height, what are we looking for?
Vertex.
Vertex. So this is find the vertex. Okay. Now looking at this problem, this function, what is the value of A?
Negative 4.9.
Good. What is the value of B?
2.45.
2.45. Now we have all the information to help us find the vertex. And we first have to start off by finding H. So remember, H is negative B over 2A, and that'll give me negative 2.45 over 2 times negative 4.9. This gives me negative 2.45 over 2 times 4.9. What is that? Is that 9.8? Let's see. Yeah, negative 9.8. Okay, and then over here, negative 2.45 over negative 9.8 gives me a positive 0.25. So remember H, well not H, sorry. The H value of our vertex. So this represents the amount of time that we're going to get to that maximum height. So this is going to happen in 0.25 seconds. But it's not done because now we take this value and we plug it into the original function to find that maximum height. So we'll say K is equal to, and this is in terms of H. So we're going to say K is equal to H of 0.25. So now you take 0.25 and plug it in for every T. So you would have negative 4.9 times 0.25 squared plus 2.45 times 0.25 plus 2. And let's see. So negative 4.9 times 0.25 squared plus 2.45 times 0.25 plus 2. And rounded to 2 decimal places, this ball is going to hit 2.31 meters. And that's what we're looking for. This is the max height. And again, if you want to prove that, well, let's see. I'll type this in. Negative 4.9x squared plus 2.45x plus 2. And that's our max height. So let's go down to what, 3 and 0. And then my x values will go from 0. And my time is 0.25 seconds. So let's go 0.5. Oh, about 0.3. There it is. There's our vertex. 0.25 and 2.31. All right. Next, how long is the ball at or above 3 meters? So based on what we found in B, if 2.31 meters is the maximum height, will this ball ever reach 3 meters?
No.
No. So the ball is never at 3 meters. Okay, awesome. Everybody go with that. Okay. All right. 5. A half pipe ramp at a skate park is approximately in the shape of a parabola. If X stands for the horizontal distance in feet from where a skateboarder starts a ride on the half pipe, and Y stands for the height in feet of a skateboarder from the ground, then the position of a skateboarder on the ramp is given by Y equals 0.42x squared minus 0.567 plus 20. Find and interpret the vertex. Ooh. Okay, cool. So all we have to do for this one is find the vertex. Maybe we can even draw a small diagram here, right? So let's say here's our half pipe. So this is where the skateboarders start. They drop in and then they land back over there, right? So there's our half pipe. So let's just say our skateboarder is somewhere in here. There we go. That's excellent drawing skills. And there's our vertex. Okay. So now all it wants us to do is find the vertex and interpret it. So based on this equation, what is a value of A?
(0.42).
0.42. What is the value of B?
Negative 5.67.
There you go. Okay. Now we just have to find H and K for our vertex. So H is again negative B over 2A, and you get negative 5.67 over 2 times A, which is 0.42. All right. And then that'll give me positive 5.67 over 2 times 42 cents. That is 84 cents. So let's see. So 5.67 over 0.84. And you get 6.75. So this is going to represent the distance from the skateboarder to a certain point on the half pipe. So this is going to be 6.75. I think it's all in feet, right? Yeah. 6.75 feet. Now to find K, of course, you plug it back into that function. So K is going to equal f of 6.75. And to save room, I'm just going to type it in over here. So it's going to be 0.42 times 6.75 squared minus 5.67 times 6.75 plus 20. All right. So this is going to be at 0.86. And this is also in feet. So all we have found by this vertex is that on this half pipe, if the skateboarder is at the vertex, then he is 6.75 feet from the drop-in, and at the vertex, he is 0.86 feet above the ground. So that's all we're saying with that. So at the vertex, when the skateboarder drops in, he's 6.75 feet from the drop-in and only 0.86 feet above the ground. Okay. That works. Everybody good with that one? Okay. The number 6. In science class, students were asked to create a container to hold an egg, which they would then drop from a window. The function h of t equals negative 16t squared plus 25 gives the container's height in feet after t seconds. Okay. How high is the window? Again, that means we are looking for the Y-intercept. So the students are about to drop the egg. They're about to. And if they haven't dropped it yet, how much time has passed?
0.
0. That's our favorite number today. So at 0 seconds, h of 0, and if you plug in 0 for every t, how high is this window?
25 feet.
25 feet. That's how high this window is. Okay. And then B, find the maximum height of the container. How long does it take to reach its maximum height? Okay, so that means you are looking for the what?
Vertex.
Vertex. But do we have to look for the vertex? Because we are dropping the egg out of a window. So what is the actual maximum height of this egg crate?
Oh. 0.
Well, if it hits the ground,
Uh-huh.
it will be
25 feet. 25 feet. I'm sorry.
it's 25 feet, right? So, I mean, if you did try to solve for the vertex, right? So, because why not stray from that tradition? Whenever you see find the maximum height, you are looking for the vertex. So if you look at this equation, what's the value of A here?
Negative 16.
And what's the value of B?
0.
0. So when you try to find H, you have H equals negative B over 2A. You'd get negative 0 over 2 times negative 16, which gives you 0 over negative 32. So H is 0, because remember that this value represents the amount of time. So at 0 seconds, you're at your maximum height, which again gives us the same exact answer. Because if you're dropping something out of the window, when it hits the ground, it's at 0 feet. But is 0 feet the maximum height?
No.
No. And again, you could prove it here. You can say, what is H of 0? And plug in 0 again, and you get 25. feet. So the answers are the same. So that's a little mind boggler, right? Okay. And then number 7. Eddie is jumping on a trampoline. His height h in feet at time t in seconds can be modeled by the function h of t equals negative 16t squared plus 20t plus 6. Will Eddie reach a height of 14 feet? Well, the only way to know that is to know how high Eddie can jump. So what should we look for? What will give us the maximum height that Eddie can jump?
Are we
Vertex.
looking for the vertex?
Look for the vertex. That's it. And if we find the vertex, we know how high Eddie can jump. And we will know if he could reach 14 feet or not. So looking at this equation, what is the value of A?
Negative 16,
What's the value of B?
20.
There you go. And now if you find H is negative B over 2A, and you get negative 20 over 2 times negative 16. That gives me negative 20 over negative 32. And negative over negative makes positive, of course. So we just do 20 over 32. And what this is saying is that Eddie will reach his max height in 0.63 seconds. But we want to know what the max height is. So you take 63 seconds and plug it in for T. 0.63. And again, just type it in over here. Negative 16 times, and I'll use the rounded version. Let's see what happens. 0.63 squared plus 20 times 0.63 plus 6. And the maximum height that Eddie can jump on this trampoline is only 12.25 feet. So, will Eddie ever be able to reach 14 feet?
No.
No. So, unless he has a friend who can bounce him that high. I'm pretty sure I've got up to 14 feet on the trampoline. Seems easy, right? All right. And then B, how tall is the trampoline? So if Eddie hasn't jumped at all, how much time has passed by?
0.
0 seconds. So when time is 0, you get h of 0. And if you plug in 0 for every t, how tall is this trampoline?
6 feet.
6 feet. That's it. Boom. Oh, I should have said this was looking for the Y-intercept. All right, guys. And those are quadratic applications. Brutal, huh? Or not too bad? Whoever's still alive out there.
Not too bad. It's just a lot of deciphering.
It is. It's
Gotta-
translating
Brain hurts.
English into algebra. It's definitely difficult. Okay. Well, That's it. We are done. So if you got questions, stick around. And if not, enjoy your weekend, right?